All right, welcome to the next video here. We're going to cover section 2.2, which is titled Determining Volumes by Slicing. And this is the next application of integrals. And so the idea in this section is that we're going to take some area, kind of like we talked about in the last video, but we're going to find its volume by rotating that area about the x-axis or the y-axis. And the methods we're going to use, there's two methods. There's the disk method and then there's the washer method. We're going to look at both of those. In this video, though, we're going to be looking at the disk method. And so the main idea is that we want to take an area like this one here in figure A, and if we were to think about this area and rotate that area about the x-axis, it would form a solid like we see here in figure C. Now the way this looks, the way we do this is a little bit more complicated. So I want to get at the idea of this by looking at an example. And so if we look at example 1, it says sketch the region bounded by the given curves. Draw a representative rectangle. I want to make sure we do that. Draw a representative rectangle and find the volume of the solid obtained by rotating the region about the specified line. And it says here the region is bounded by y equals x squared plus 1, x equals negative 1, x equals 1, and y equals 0. And we want to rotate that about the x-axis. So much like the problems that we looked at in the last chapter, or the last section I should say, we want to start by sketching a graph. And so we've been doing this in Desmos. I'm going to assume you can do that on your own now. And I'm going to go ahead and start sketching this. I think we should be good to do that. So I'm going to put an axis in here. And first one we have is y equals x squared plus 1. When x equals 0, this is equal to 1. When x equals 1, we get 2. And when x equals negative 1, when x equals negative 1, we also get 2. Let me go ahead and put those points on there. And this is our parabola. This is 1, 2, negative 1, 2. This is the curve y equals x squared plus 1. And then we want to graph x equals negative 1. That's a vertical line that goes through negative 1. That's x equals negative 1. We also have x equals positive 1. And then the last curve we have is y equals 0, which is the x-axis. So it's bounded here below. So we basically have this area right in between that curve. Right in between all four curves. So you might be able to kind of picture the shape we'd get if we rotated that about the x-axis. I would kind of think of it as an hourglass. If we just rotated it about here, kind of something that looks a little something like this. Actually, let me draw it the other way. Since it's rotating horizontally, probably something more like this. Now, it says to draw a representative rectangle. Like we did in the last section, we still want to think of this as, okay, is the problem going is this a region where we have a left to right or a bottom to top? And I think this is going to be easier as a bottom to top. So our representative rectangle is going to go vertical. Representative rectangle is going to go vertical. And its thickness is going to be dx. And I want you to think about what the representative rectangle is going to look like when it is also rotated about the x-axis. So let's draw what that is going to look like. So we could say when rotating the representative rectangle about the x-axis, what do we get? What shape is that going to be? Well, if you said a disc, you would be correct. It kind of looks like a disc. We get a disc. Take that rectangle and you roll it and you rotate it around and you get something that looks kind of like this. And that disc can be thought of also as like a really short cylinder. So if you think about the volume of a cylinder, let's remember what that is. Recall the volume of a cylinder is V equals pi times the radius squared times the height. So if we think about this, we definitely have here cylinder. Here's the radius. And then the height would be this thickness down here. It's, you know, that thickness right there. Be right like this. So that thickness right in there, that's our height. And in this case, that's basically the thickness of the representative rectangle. So our height is going to be dx. And then our radius is the distance from the x-axis up to the curve. So our radius is that y distance. This is y. And so what does that mean about our formula here? V is going to be equal to pi times the radius squared, which is y squared, times the height, which is dx. So now that's just the volume of one of these discs, which just makes up one slice, right? This disc of this representative rectangle is just one slice of that total volume, and that's where the integral comes in. So if you take the volume of this disk and add it to the infinite number of other disks that make up this total volume, we get the total volume of the region that's formed by the revolution or the rotation. And so to find that total volume, if you will, we want to take this quantity that we just talked about, pi y squared dx, and we want to integrate it. And where do we want to integrate it from? Well, think about moving that representative rectangle from all the way on the left of that green area to all the way on the right. So we're going to be going from -1 to +1. -1 to +1. And there is one issue here because this integral is going to be with respect to x, yet we have y squared here. Well, what is y in this case? That's that top curve. That's this curve up here that bounds that, and we know that y is equal to x squared plus 1, so we're going to go ahead and plug that in there. And so that does change our integral a little bit. We can move the pi out in front. We get the integral from -1 to 1. And then in place of y, we're going to put x squared plus 1. And then we, of course, can simplify that integral. That's going to become x to the 4th plus 2x squared plus 1. And then we can take the antiderivative. Plus 2/3 x to the 3rd plus x, evaluated between -1 and +1. This is going to give us pi times 1/5 plus 2/3 plus 1 minus -1/5 minus 2/3 minus 1. Which, if you do the math there, that gives us 56 pi over 15. Whatever those units are, this can be units cubed. And so this method that we just came up with here, where we took a representative rectangle and we thought about rotating that about our axis, that gave us a disk. We actually called this the disk method. It has, which is not surprising. It would make sense, I think. And so it's kind of outlined here in the figure below. You notice you take that representative rectangle and then you rotate it about the x-axis. You get a disk. But it's not just that little area, it's the entire area that was enclosed. So if we take that entire area and rotate it around, or we take a bunch of these disks stacked together, we get a volume. We get a volume like we see here in part D. It's a solid of revolution. And so the method here, it's called the disk method again. And here is the formula again that we're going to use. And that's when we rotate about the x-axis. Of course, it's not always that we rotate about the x-axis. Sometimes we're also going to rotate about the y-axis. So things do change a little bit. And example 2, we'll go over in the next video. We'll kind of show how that works. All right. Thank you.